Good afternoon and welcome to our tour of outer space here on the Morrison Planetarium Facebook page and the OpenSpace YouTube channel. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences in San Francisco. It's a great pleasure to be joining you today for a little bit of a tour of outer space as the title of the program promises, where we start relatively close to home here on Earth, maybe visit a few places in the solar system, and then share some of the cool data sets that are available in the OpenSpace software platform. OpenSpace is an open source software program that you can actually download and run for yourself. And that's what we have showing here, showing the International Space Station. And this is a place that I like to start out my presentations because it's a nice human scale. You can imagine that's about the size of a football player. Oh boy, we're off to a good start already. Football field, and it actually, because soccer fields and football fields are about the same size, it doesn't matter if you're tuning in from the UK or Europe or wherever, of all the places in the world that call football something other than Americans do, it's roughly the same size. It's 100 yards, 100 meters, whichever you prefer in length. And there are people on board the International Space Station. So it's a good place to kind of begin our journey because we're going to go places that are a lot farther from home and a lot kind of harder to wrap our heads around. And so it's good to start with something that's kind of a more human scale. So again, if you can imagine, there are people on board. In fact, as I like to point out, one of my fellow grad students from grad school, Shannon Walker, is aboard the International Space Station right now. And as you can imagine, she had to do a lot of hard work to get there. She's trapped in a tin can a few hundred kilometers above the surface of Earth, whereas I'm here in the comfort of my own living room talking to you folks. So you can decide who got the better end of the deal in terms of our graduate education and outcomes. But what I did want to talk about actually is, before we let too much time pass here, is that the International Space Station is actually here. We're showing it as where it was in its orbit about half of an orbit ago, because it's right over California. So in fact, we're flying over, or they were flying over San Francisco-ish right now, or about 45 minutes ago. And it's easy from this altitude. And if you go on the NASA website, you can see all these amazing images that astronauts take of our own home planet Earth, really the most beautiful planet in the universe, at least that we've found so far. And of course, beautiful because we live here. But it's this amazing perspective on our home world because it's relatively close by. It's a few hundred kilometers, few hundred miles above Earth's surface. And that's as far as humans go out into space these days. What's great about this tool, OpenSpace, and we'll share some links for you to be able to download it and play with it yourself, but also just about this sort of concept of a virtual universe, is that we can exceed the speed of light, we can exceed the technology that it takes to launch spacecraft into orbit around Earth and beyond, and go much, much farther out into the universe. So we pulled away quickly enough so it looks like the International Space Station kind of plummeted into the Mojave Desert. That's not the case. It's really just that we're pulling away from our location in orbit around Earth. I always like to point out there's no up in space, so we're kind of pulling away with the North Pole kind of right underneath us, and kind of a different perspective on our home planet than one normally gets. And then in the background, you can kind of see the Milky Way. And in fact, we kind of lucked out. We're actually pointed right toward the locations of the closest star, Alpha Centauri, and some beautiful stars in the southern hemisphere, as well as this remarkable, beautiful kind of diaphanous starry starscape that you can see especially well from the southern hemisphere, but also on a clear night sky from here in the northern hemisphere. This beautiful view of the Milky Way, what struck ancient Greeks as looking a little bit like spilt milk, is in fact the light of literally hundreds of billions of stars. They're just so far away that they kind of blur together to form this sort of milky haze in our sky. And what we see here is these dark clouds. And in fact, in the southern hemisphere, these dark clouds that are obscuring the light of more distant stars are so prominent in the sky that instead of playing connect the dots with the stars and talking about constellations of stars, many cultures refer to these dark regions of the sky as images that they describe and talk about. So We're going to talk a little bit more about the Milky Way, which is why I wanted to sort of jump on the opportunity to describe it as we're leaving Earth behind. But just to go back to my main point, that our astronauts, brave and amazing people that they are, travel right now a few hundred kilometers above Earth's surface. But even our most ambitious astronauts, or the ones who had the opportunity back more than 40, like about 50 years ago, to travel farther out into the universe. The farthest any humans actually made it out into the universe is kind of represented here. We have this line that connects to Earth is the orbit of Earth around the sun, and this sort of partial circle here you see is the orbit of Earth's moon around our home planet Earth. The moon, Earth's moon, is the farthest any human beings have traveled out into space. And if you think about that distance is about 250,000 miles, 240,000 miles, about 400,000 kilometers, if you are more civilized and use those units. And that's a pretty mind-boggling distance even of itself. It's several times around Earth. If you were to circle Earth, it's if you imagine having a car for a really long time, you might drive it 250,000 miles. And it took astronauts 4 days to travel that distance. But in terms of astronomical distances, it's not very far at all. The distance from Earth to the sun is about 1.5 seconds in terms of light travel time, because light travels at a constant speed, 186,000 miles per second, 300,000 kilometers per second. So it traverses that distance between the Earth and the moon rather quickly. The sun, which you can kind of see as a sort of weird orangish dot in the middle of the hazy glow that we use to represent its location that make it easy to spot at a greater distance. The sun is about 8.5 minutes away in terms of light travel time. And so the moon, very close to home, about kind of like a pause in conversation between light leaving the moon and reaching our eyes on Earth. And the sun, 8.5 minutes, it's more like a quick lunch, perhaps, from the time light leaves the sun to when it reaches Earth's surface. And that light travel time is something that we're going to reference quite a bit as we get farther and farther from home. So I already kind of previewed that we will be talking a little bit about the Milky Way galaxy, the kind of collection of stars in which we live. But before we get too far from home, we usually have people asking for maybe some preferred destinations in the solar system. So if you have a place that you'd like to visit in the solar system, just to give us a little bit of sense of scale, please put that in the chat. And also, if you have any questions that pop up at any point during the program, please feel free to put those in chat, and I'll try to answer them live as we go along. Or if not, we can answer them in comments after the fact. I'm not actually seeing any questions, which is startling me. It makes me think that I must be a terrifying presenter, since we normally get so many questions and requests to visit different places in the solar system. Oh, wow, to a nebula. Okay, wow, that's someone talking after my own heart. The request to go to a nebula, I will bookmark that and get to that a little bit later when we get a little farther from home. Okay, well, we have a request for Neptune. So that's a great request there. The inner planets that you can just barely see here, Mercury, Venus, Earth, and Mars, are all kind of huddled sort of close to the light and heat of the sun. Jupiter, Saturn, Uranus, and Neptune are the giant planets kind of out toward the outer reaches of the solar system. So Neptune, the most distant planet, let me go ahead and target Neptune. And actually, to do that, I'm going to go ahead, because a couple points here. I'm going to reveal the interface that we use to interact with the OpenSpace interface here. And what we can do, so I'll give you a little bit of an OpenSpace lesson, is if you want to visit one of these planets, you can use this little symbol to target it, and that way I'm a pretty good pilot through interplanetary space, but it's a little bit easier to have the computer do the navigating when you want to go to something as specific as a planet. So let me go ahead and take us to Neptune. Neptune, I mentioned Mercury, Venus, Earth, and Mars. Those are kind of rocky planets in close to the sun. Jupiter and Saturn are kind of the giant planets in our solar system, in the sense that they are larger even than Uranus and Neptune, the two outermost planets. And Uranus and Neptune are also, whereas we often call Jupiter and Saturn gas giants, sometimes call Uranus and Neptune ice giants. And that's because they're very far away from the light and heat of the sun. And yet, Neptune in particular is fascinating because the winds in the upper atmosphere of Neptune, and here it's kind of important not to think about these outer giant planets as very much like Earth or Mars or the Moon, where you have a solid surface. Instead, these are almost entirely gas. And even these ice giants have a very thick outer kind of atmosphere that encircles them. With Neptune, one of the things that we found absolutely amazing, and this map that we're showing we don't know exactly what Neptune looks like right this very moment. But when we visited Neptune back in the late 80s, we did find what was called a great dark spot. And the clouds of Neptune actually showed wind speeds that far exceeded what we kind of imagined would be the case in the outer solar system. On Earth, winds are really driven by the energy input from our sun. And since Neptune, as our questioner called it, this mysterious planet out at the edge of the solar system, is so far away from the light and heat of the sun, we imagined that it wouldn't have kind of the energy, the dynamics to kind of power this kind of high-speed winds. But in fact, we see winds exceeding 1,000 miles per hour in the upper atmosphere of Neptune, which makes us wonder kind of what's going on at this distant world. Unfortunately, Neptune is a planet that was visited only once by the Voyager 2 spacecraft. Jupiter and Saturn have kind of lucked out in terms of the giant planets. They've both had their own individual missions that visited them. Galileo and Juno are the two missions that have visited Jupiter. Saturn had the Cassini mission, which orbited the Saturn system for many years. So we understand those systems a little better than Uranus and Neptune, which have never kind of lucked out and had their own specific missions visiting them. So now we're kind of looking here at a view of our solar system. And since we talked about Neptune, it's a good measuring stick. I mentioned the light travel time compared with Earth's distance to the moon, compared to Earth's distance to the sun, second and a half in terms of light travel time from Earth to the moon, 8.5 minutes from Earth to the sun, and vice versa. The diameter of Neptune's orbit is about a little less than 8 light hours. So it takes about 8 hours for light to travel from one side of the solar system to the other. Now, if you compare that to a second and a half, like I said, kind of a brief pause in conversation, or 8 minutes, maybe a quick lunch, 8 hours, well, that's a good night's sleep. Not bad. What's really interesting is if you want to compare that then to the distance to the nearest star, Alpha Centauri, that's about 4 light years away. So the difference between interplanetary distances is measured by the diameter of Neptune's orbit, and interstellar distances as measured by the distance to the nearest star is the difference between a good night's sleep and a high school or college education. So it's a vastly different set of distances when we start to talk about the distances to the star. And actually what always blows my mind, because we've sent spacecraft, like I said, the Voyager 2 spacecraft visited Neptune, a couple spacecraft have visited Jupiter, a couple spacecraft have visited Saturn. We understood these places by sending spacecraft to visit them. And in fact, we can show you the trajectories of some of those absolutely fastest spacecraft that we've ever sent out into space. The trajectories here showing the, let me go ahead and just make a little tweak here to kind of center things once again. The trajectories here showing the New Horizon spacecraft here, which visited Pluto. That's the only one of these spacecraft that was launched in the last 20 years. All of the others were launched back in the 1970s. So if you look at, this is the Voyager 2 spacecraft that visited Neptune and Uranus, as well as Saturn and Jupiter. The Voyager 1 spacecraft visited only, oops, I lost it. The Voyager 1 spacecraft here visited only Jupiter and Saturn. And then the Pioneers 10 and 11 spacecraft were launched a little bit earlier than the Voyager spacecraft and also visited Jupiter and Saturn. Now, those spacecraft, these 5 spacecraft, are like the fastest nuts and bolts objects we've ever sent out into space. And if you pull back here a little bit, you'll see that this is where they are right now. We're kind of extending their trajectories out into the space to show how far they've gone in the last 50 some odd years, 40 some odd years. None of them have traveled as far as light travels in a single day. Because remember, it's about 8 light hours across the diameter of Neptune's orbit. So our spacecraft haven't made it very far into the universe. And yet, we understand a phenomenal amount about the universe around us, and we understand it by studying light from these distant objects. So first of all, as we pull even farther away from home here, those trajectories of those fastest objects are kind of recede into a single sort of blurry point here. We've now made the sun, we were artificially dimming the sun. So we now made it as bright as the other stars. So we're actually drawing all of the stars with a consistent sort of brightness to them. And as we rotate around here, you can see a familiar constellation of the Big Dipper, for example, now with the sun superimposed in front of it because we've traveled maybe a light year or two away from our location in the universe. And before we get too far away, I just want to return to that view of the Milky Way, which is kind of coming into view from the left here. And I want to point out that in addition to these kind of the individual stars that we see lining the really throughout the night sky, but particularly the many, many stars in the Milky Way, we actually also see some like clumps and clusters of stars. And actually, it's connected to the idea of nebulae. So for the person who asked for a nebula, that's just a reminder that I haven't forgotten. I haven't forgotten you. I'm trying to figure out how to show you a good nebula, but we'll try to get there. But let me kind of speed up our rotation here and get us to a couple interesting parts of the night sky, because we actually see, and oops, that was a little too fast. Sorry about that. We see the constellation Orion here, which is easy to spot with the 3 stars in the belt of Orion the Hunter, 2 stars in his shoulders, and basically he's kind of upside down here. This is his head. He has a sword dangling from his belt. That's an image that's constructed from the northern hemisphere of Earth. What I wanted to point out, though, is down here in our screen below Orion, you can see a group of stars here in kind of a V shape. We talk about that as the head of Taurus the Bull, which is the constellation that's sort of doing battle with Orion. It's kind of weird that a hunter is hunting a bull, but yeah, that's what's going on there. And then the little clump of stars here called the Pleiades, or the 7 sisters, those actually mark out the kind of other end of the bull and also part of the constellation Taurus. These are clusters of stars that they just happen to be in the same part of the sky. They're actually all close together in space. This bright star that forms a kind of red bloodshot eye of Taurus the Bull is actually in the foreground. We'll see that in a minute. It's called the star Aldebaran. Whereas the rest of the stars are actually part of a cluster of stars. We're all born together. They're kind of like a group of teenage stars here. And then down here, the Pleiades is a cluster of stars, again, that form together, but even younger than the Hyades, a little bit farther away. And they, again, form together, and they're more like, not quite infants, but they're pretty young stars. This is more like a nursery. This is more like maybe some teenagers hanging out at the mall. So the stars form together in clusters, and we can actually, I'll go ahead and show you the interface to our software once again. We can highlight the locations of these in the sky, and actually, as we'll see in a moment, we'll highlight their locations in 3 dimensions. So you'll see here that the Hyades have this kind of big green circle around them, the Pleiades as well. There are actually lots of other little clusters of stars that we only see in telescopes. They're not as easy to spot as the Hyades or the Pleiades. But what's cool about this is that you can kind of see the pattern already. If you look at where these clusters of stars are, you'll notice that they kind of line the Milky Way. So there are a few above and below the plane of the Milky Way, but most of them lie right along the sort of milky, hazy part of the sky. And just as a little bit more information, you'll see this as we pull even farther away from home. You can see that some of the circles are larger than others. The ones that are larger are a little closer to us, and the ones that are smaller are farther away. So if you see a big circle like this one on the upper right-hand side, you're seeing a cluster, a representation of a location of a cluster that's relatively close to home. So those are what we call open clusters of stars. They're very young stars, kind of, like I said, sort of nursery school age, or maybe as old as like teenagers, but they're young stars that sort of haven't made their way out into the solar system just yet. So remember, open clusters, but now I want to show you a different collection of stars called globular clusters. Now, these are much older collections of stars, much denser. Open clusters may have a few thousand members inside them, but globular clusters may have hundreds of thousands, millions of stars inside. And here, these are represented by these kind of yellow pentagons. You'll notice, well, you might say, oh, well, wow, there's a lot of them here along the Milky Way. Maybe something similar is going on to the open clusters. But then as you look around, first of all, we don't see as many globular clusters, but then you notice that actually there aren't really any over in this part of the sky, or not many at all. And if we turn around, kind of sort of just panning around the sky, you'll see that there are basically none over in this direction. You kind of have to face over this way to see globular clusters. And what I'd like to do now is kind of pull away from our location. I've already talked about the Milky Way, this hazy band of stars with hundreds of billions of stars so tightly packed that their light from these hundreds of billion stars kind of blurs together to form this hazy band in our sky. And now I just want to pull away and keep the locations of those globular clusters highlighted. This, as it turns out, was our first clue that however much we humans love to think that we are kind of the center of the universe, location of globular clusters was one very serious initial clue that we are not at the center of everything, because as we now show the Milky Way galaxy as seen from the outside, you can see that the globular clusters are all kind of, they're actually in orbit around the center of the Milky Way galaxy. We are not at the center, and so all of the globular clusters sort of appear to be in one part of the sky, often the direction of the center of the Milky Way galaxy. There are also, many of them are above and below the plane of the galaxy. There are different ways to think about globular clusters. You can think of them as kind of like leftovers, remnants from the formation of our Milky Way galaxy. And so before our Milky Way flattened into a pancake, as you can see, the disk of the Milky Way as we pass through it here, these kind of leftovers are still kind of tracing out what we call the halo of the Milky Way. But now let me go ahead and put up our open clusters at the same time. Now it's a little harder to see what's going on here. Let me see if I can make our open clusters a little brighter. Actually let's see if we can do this. So the green dots now are kind of tracing out the locations of open clusters. And you'll see that they're all very much inside this disk of the Milky Way. So these young stars, and they are much younger than the globular clusters, are all located in the disk of the galaxy because that's where young stars are forming. Older stars, like you find in the globular clusters, which I don't really mention, but in addition to being much larger than the open clusters, the globular clusters, these kind of hexagonal ones, are actually stars that are individually much older than the stars in the open clusters. Let me go ahead and take away the the globular clusters. So we just have those open clusters again. And again, notice that they are all kind of located in the plane of the Milky Way, not very far above or below the plane, but instead kind of tracing out the very flat plane of the galaxy, because this, again, is where young stars are forming in our galaxy. So I told you how far our spacecraft have made it away from Earth. And the person who just asked this question, how do we know what the Milky Way looks like, is right on track to where I was going with this. Because we've never had a spacecraft that could go outside our Milky Way galaxy to take a look at it. We've never had an image of our own galaxy like the one that I'm showing you here. This image of the galaxy is based on our observations of other galaxies, so other spiral galaxies like our own, and based on data like the open cluster data and the globular cluster data to understand where the arms of our galaxy reside, because as it turns out, those open clusters, those young stars, are typically found along the arms of the galaxy. And they actually see, I might also be able to bring up, I apologize, not all of this is probably showing up terribly well on the streaming video. So I apologize for that. I probably should have done a little bit more fine tuning of this. But we can also highlight here what are called OB associations. These are the very youngest stars, even younger than some of those open cluster members. This isn't even really, these aren't even like teenagers or nursery school attendees. These are more like infants, but they're like loud, noisy, bright, obnoxious infants that are easily observed from great distances. And you can see again that they kind of trace out locations of where our nearby spiral arms are located. But to kind of fill in that question then, using other wavelengths of light, for example, radio waves, we can actually see things. And let me see if our H2 regions show this nicely. Let me take off our open clusters and our OB associations. H2 regions are now finally getting into this realm of the nebulae that we were talking about earlier. You can see that we can observe these at much greater distances. And again, we can figure out basically the layout of our galaxy by observing in multiple wavelengths these different objects, many of which are associated with places where stars are being born. So I'm actually realizing here that I was trying to figure out if we have our nebula model in here, and I realized we do not. So unfortunately, I can't actually take you to a nebula. I'm going to say that behind the scenes, we have the amazing and talented Mary Holt, and if she might be able to look up, for example, an image of the Orion Nebula or another star-forming region and put those as comments in the chat. You can pull up some of those images. I'm afraid I just don't have the ability to do it in the software. It's a function that we've been talking about adding, but I was trying to look behind the scenes, and I kind of hoped we had a model of one of the cool star-forming nebulae, namely the Orion Nebula, but that doesn't seem to be loaded in my system at the moment, so I can't take you to visit that. So I'm going to unfortunately not be able to directly address that question of nebulae, except to say that those nebulae, particularly something like the Orion Nebula, are the origins of the stars that end up populating the arms of the Milky Way galaxy, and they're kind of the beginning of this narrative of what turns those nebulae, are kind of like the nurseries of stars that form those bright young OB associations that I showed you, eventually form the clusters, those open clusters of stars, and then basically are the engine that drives the formation of stars in our own galaxy. So we're kind of getting close to our time here. So I just want to note that since we were talking about how we understand what the Milky Way looks like, I won't go too far out into the universe around us, but I just want to make reference to how many other galaxies we do know about in the universe. And so what we're showing here now, all of these little dots are no longer individual stars, or they don't represent the location of clusters of stars, or what I called H2 regions of the gas that are used basically eventually form stars. Instead, these individual points represent the locations of distant galaxies. Many of them are as big as the Milky Way, or even a little bigger. And many of them look a little bit like the Milky Way as observed from our location. So we can see the spiral arms of the Milky Way, of these other spiral galaxies. And that's how we deduce that we live inside a spiral galaxy. And we can observe open clusters and globular clusters in these other galaxies. So we kind of know that we're looking at sort of mirror images of ourselves out in the universe. And that information then is fed into our perspective on the Milky Way galaxy. And so even though we don't know exactly what the Milky Way looks like, here we sort of start with an image of a similar galaxy. And then we actually, working with astronomers in Japan who modeled the evolution of galaxies using computer models. We use that as the basis of a three-dimensional model that is then used to depict the Milky Way galaxy as a whole. But when you get right down to it, the part of the galaxy that we know the best is really the part that is closest to home. And so what I'd like to do is just kind of take us back in toward our own solar system. So we have, once again, this kind of view of the Milky Way, of that amazing disk spiral galaxy in which we reside from the inside. And as we approach the sun here, and before we get close enough to see our planets, I just want to kind of once again kind of scroll around to get a view of the Milky Way from the inside. Because what is amazing is that by studying these different objects in our Milky Way, we can transform our perspective of our galaxy from this view from the inside, clouded by clouds of dust that get in our way, but with observations that extend across many wavelengths of light to kind of fill in our perspective of what the galaxy is like around us. So kind of cool that even though we can't send spacecraft out to observe our Milky Way from the outside, we can still piece together what it looks like by studying the light from these distant objects. So with that, we'll go ahead and pull in back close to home, close to the sun. Oops, that's a little too close to the sun. I actually want us to go to Earth, not to the center of the sun. So let me go ahead and tweak our targeting here and bring us in close to home, back to our own home planet Earth, with the International Space Station in orbit around it as far as physical humans get to go out into space these days. But thanks to our technologies, being able to explore our digital universe and our virtual universe using our amazing tool, OpenSpace, can take us on journeys like the one we just took outside our own galaxy to think about what the universe looks like from a perspective very different from what we have from here on Earth. So with that, I want to thank you for joining us today. If you have any other questions, please feel free to ask them now. If I have a chance, I can answer them, or we'll go answer them in chat. Happy to do either one. And I'll also note that if you have a chance, we would appreciate it if you could take a quick survey about OpenSpace. This is actually an open source platform that, again, you can download and use for yourself. We'll share that link in chat and maybe put it up on screen as well. But also, it's funded by NASA. So we want to know if people are using it, what people think of some of these programs. So if you have a chance to share your perspective, we're going to put a link to a survey right here on the main screen. So if you can go to that and give us some input, we would really, really appreciate it. So again, thank you for joining us here for this tour of outer space on a Wednesday afternoon. I will let you know we're going to actually be opening Morrison Planetarium to the public very soon. And so this is one of our final tour of outer space that you'll have a chance to ask questions in quite this way. But starting at the end of the month, you'll actually be able to tune in at the same time, 4:30 p.m. Pacific time, on either the Facebook Live Morrison Planetarium page or on the OpenSpace YouTube channel. And you'll actually be seeing a simulcast from Morrison Planetarium in San Francisco. You'll be joining an audience virtually as we do a similar program, taking people out from International Space Station or Earth on out to the outer limits of the universe. So I hope you'll join us for some future Wednesdays, and certainly join us next Wednesday when I'll be able to host once again our tour of outer space from here on Facebook Live and YouTube. Thanks for joining us.